Okay, so we would like to show Minkowski's inequality. So we have a number p which is greater than 1. We consider it fixed. And then for any real numbers, ak and bk from 1 to n, we have the inequality that we have just written down. And in order to prove this inequality, what we need to do is use Hölder's inequality. And let me remind you what Hölder's inequality says. It says that if you have, let me use different letters here. So if you have U1 and V1 all the way to UN and Vn, then this in absolute value is less than or equal to the sum of the UIs or UKs, it doesn't matter, from k equals 1 to n to the pth power, all raised to the 1 over p times the sum from k equals 1 to n of vk to the pth power of, I'm sorry, to the qth power. And all raised to the 1 over q power, where 1 plus p over 1 plus q is equal to 1. Okay, and what I would like you to notice here is that if you replace U1 and V1 by their absolute values, I'm sorry, the UKs and the VKs by their absolute values, then this also gives you the seemingly stronger inequality, but it's not really stronger, it's pretty much the same thing. Less than or equal to the same. Okay, so this will be our main tool for showing the Minkowski inequality. And we will make use of this exponent q, which is related to p by the condition 1 over p plus 1 over q is equal to 1, even though it's never mentioned explicitly in the Minkowski inequality. Okay, so why don't we proceed with the proof? The proof is actually very, very interesting. And we start again with a very trivial observation. If the left-hand side is equal to 0, so proof. If the left-hand side is equal to 0, there's nothing to prove. We're good, right? Because we have 0 is less than or equal to the sum of two non-negative quantities. So assume that the left-hand side is greater than 0. And now we are going to do a series of acrobatics. I think this is one of the most entertaining proofs of inequalities that you can find. So I start, let's enjoy it. So I start with the sum, right, that appears inside the 1 over p power, which is precisely this one. And now remember that p is greater than 1, so I can still rewrite this as sum from k equals 1 to n. Okay, this is something trivial. The important thing is that both exponents are positive here. So ak plus bk to the first power. And this is less than or equal. Let me go to the next line. In fact, you will see that I will need to give myself some space in order to carry out of this. So k equals 1 to n of ak plus bk to the p minus 1 times the absolute value of ak plus the absolute value of bk. Okay, so we just replace AK plus BK in absolute value by the sum of the absolute values. And that, of course, reinforces the inequality because of the corresponding triangle inequality for real numbers, right? So now we write this as two sums. So here's the first sum. Plus the second sum. And now we apply the Helder inequality where, and this is why I wrote it with U's and V's. So pretty much our U's for the first sum are going to be these numbers with the exponent together. The V's are going to be these ones. And for the second sum, we're going to have these numbers as the U's and these numbers as the V's. So this will be less than or equal. So I'll put the less than or equal down here to a product where I will have the sum of k equals 1 to n of AK plus BK times P minus 1. And now I will raise the whole thing to the qth power, which amounts to multiply by q. And I will take the 1 over q root of this. It doesn't really matter to which one you apply it. I mean, in Helder's inequality, we apply to first to the we put the q exponent to the uk's. We could have done this to the vk's. It's totally symmetric, times the sum from k equals 1 to n of ak to the pth power times 1 over raised to the 1 over p. And then we have a very similar sum where the only thing that changes is that now we have the pk. So we have sum from k equals 1 to n of ak plus pk to the p minus 1 times q, all raised to the 1 over q, multiplied by the sum from k equals 1 to n of the bk's to the pth power, all raised to the 1 over p. And now, the first sum is common to both of the terms. So we really have sum from k equals 1 to n of ak plus bk. Here I have a little surprise for you. So before I write the exponent, let's actually see what it is. And there are different ways to see this, but let me do it somewhere here. So I want to know what is p minus 1 times q. And there, like I said, there are maybe better ways to see this, but I really like to do it this way, to multiply and divide by p. So I have times pq, right? And then the first one is 1 minus 1 over p times pq. Yes, but 1 over 1 minus p is 1 over q times p times q. The q's cancel each other, and what you get is p. Surprise, surprise, right? I mean, everything works here like a charm. So this is raised to the 1 over q. And of course, we have the non-common parts, which are k equals 1 to n. Plus, actually, this is all in here, plus another sum. Like so. Okay, so now let's recap. What have we proven? We have proven that the initial sum and of the kth powers, and please note that there was no exponent here, is less than or equal to this sum, to the same sum, in other words, but we're actually raising it to the 1 over q power. And the whole thing is multiplied by this sum of sums. Oops, sorry about this. Let's get rid of that. Okay. And so all you need to do is divide both sides by this. Because once you divide both sides by this, what do you get? You get sum from k equals 1 to n of ak plus bk to the pth power. And that supposedly was all to the first power. But now that you divide by 1 over q, you subtract 1 over q. And this is less than or equal to the sum that really remains on the other side. And that's pretty much the end of the story. Because simply this thing right here is simply 1 over p. And that's precisely what we wanted to show. This is really a very entertaining proof. I hope you enjoyed it. You have to really try to remember Hölder's inequality and then try to do it yourselves to see the fun in proving this inequality. And that's all. Thanks for watching.